key encryption. So when we discussed at the very beginning of this course private key encryption schemes, we saw general constructions that can be modified to lead to very efficient constructions in practice. So there is no problem encrypting megabytes within a few seconds, or milliseconds sometimes. So these things are very efficient, but they need these shared secret keys. So before two people can securely communicate, confidentially communicate using private key encryption schemes, they need to have agreed on shared secret. So this requires then methods for key distribution or key agreement. And those methods exist. And in fact, what we discussed today, public key encryption can lead to such methods for key distribution or key agreement. But public key encryption can also be used as an alternative to private key encryption schemes because they don't need any shared secret keys at all. There are other techniques, the problems with it, but they don't need shared secret keys. However, they are significantly less efficient than private key encryption schemes. So whereas in private key encryption schemes, you can easily handle megabytes efficiently or even gigabytes, that's certainly not the case with today's public key encryption schemes. Hence, we have advantages for private key encryption schemes, we have advantages of public key encryption schemes. So in practice, what we do, we often use a combination of these two techniques. As I said, one combination is that you use public key encryption for key distribution or key agreement. But another alternative is that you use a technique of so-called hybrid encryption that actually combines the two properties directly, the two advantages that each of these encryption types has separately. And we will discuss in this course also hybrid encryption and see how we can combine securely private key encryption schemes and public key encryption schemes. So then what is the content of this lecture, of this part? As usual in this course, we want to construct these primitives from general assumptions, from the existence of certain types of objects that we can instantiate in a variety of ways. And in this case, we show how to construct secure public key encryption schemes from so-called trapdoor permutations. This yields then, first of all, again, the public key variant of CPA security, chosen plaintext secure schemes. And then obviously, as I said, as in the case of private key encryption schemes and public key encryption schemes, what we really would like to choose is chosen ciphertext security. But chosen ciphertext secure schemes, constructing them for public key encryption schemes turns out to be much harder than for private key encryption schemes. In the private key setting, we saw that we can combine CPA secure private key encryption scheme with a message authentication code in the encrypt and authenticate way to obtain CCA secure private key encryption schemes. This technique doesn't work at all in the public key setting. So we have to use different techniques, and all the techniques that you know are rather complicated. And here on the slide, I said that in this course, I show a construction based on so-called non-interactive, non-interactive zero-knowledge proofs. Actually, I will probably do some somewhat different construction that's based on so-called identity-based encryption schemes. Both have their uses, and there is also basically a third technique. So there is a technique based on non-interactive zero-knowledge proof. There is based on identity-based encryption, and then there's so-called hash proof systems. And I will pick one of the three, and I think I will pick IBE because that's the easiest to explain. IBE, identity-based encryption schemes, are rather easy to explain, whereas non-interactive zero-knowledge proofs, although extremely important, are somewhat more complex and abstract. And also we will present, of course, hybrid encryption and its secret. Okay. Okay, what is so first of all, let's start with the syntactical definition of a public key encryption schemes. And as you see, a public key encryption scheme is related to private key encryption schemes in a way similar to the relation between signature schemes and message authentication codes. So a public key encryption scheme consists of a triple of algorithms, key generation, encryption, and decryption. All of them are probabilistic polynomial time algorithms, although the decryption algorithm in general is a deterministic one, but we allow it to be probabilistic overall. The key generation algorithm on input 1 to the n, so the security parameters 1 to the n, outputs a pair SK, PK consisting of a public key, PK, and a secret key, SK. And we require that the length of SK and PK, say in bits, is at least n if we use the security parameter 1 to the n. So the key generation algorithm in public key encryption schemes plays the same role as it has the same input-output behavior as the key generation algorithms in digital signatures. Then the encryption algorithm on input 1 to the n, a public key PK, and a message m and 0, 1 star, say, outputs a ciphertext C, and we denote this by C is the encryption of m under public key PK. And I denote this left pointing arrow because the encryption in general is really a probabilistic algorithm, so it uses randomness. So this C here is not a fixed value. There can be many ciphertexts corresponding to a pair of message and public key. So it's a random variable over the random choices made by the encryption algorithm. Then the decryption algorithm on input 1 to the n and secret key SK and ciphertext C outputs a message M or a failure symbol. So we allow it to fail. This will become important when we look at CCA secure encryption schemes. And again, we denote this by this equation. So M is the decryption of C under secret key SK. Again, the decryption algorithm may be probabilistic. So this is again a random variable. In most cases, this decryption algorithm is actually deterministic. It's also, as I said, allowed to output a failure symbol, which is not a message. So its failure symbol is not a 0, 1 star sequence. And as usual, we have the correctness requirement, namely, we require that for all integers n, all pairs of secret and public keys generated with gen on input 1 to the n, all messages m, we have that if we first encrypt m under public key PK and then decrypt under the corresponding secret key from this pair here, then we get back our original message with probability 1. And the probability is overall random choices. The random choices made in the key generation algorithm, the random choices made in the encryption algorithm, the random choices made in the decryption algorithm. So this is not allowed to fail. So no matter how you choose the secret and public key, no matter what kind of randomness you use in the encryption and in the decryption, at the end you must have this. Or we get this failure symbol back. But this typically means that this is not, sorry, we do not get the symbol back. If we encrypt correctly and decrypt, then we should get the message M back. But the decryption may get something else than the encryption of a message, and then it may output a failure symbol. But if we give it a correctly formed ciphertext, and then we decrypt it with the corresponding secret key, get the message M back. So this is exactly as in the private key setting. The correctness is as in the private key setting. Okay. Now, how do we use these things? Okay, let me just one more remark. Of course, here in the previous definition, I said that M is from 0, 1 star. As usual, often we first design these things for messages that come not from 0, 1 star, but from a finite subset, say 0, 1 of L to the n for some fixed function L. And then we say that this is an encryption scheme for messages of length, fixed length or length all of that. This is all typical stuff that we have seen already numerous times. Okay. Now, how do we use these things? This is similar to the picture that we saw in the digital signature case. But remember, with encryption scheme, we want to ensure, of course, confidentiality, not authenticity. So again, we have a scenario where Alice and Bob want to communicate. So in our scenario, we want that we look at the case where Alice wants to send a message confidentially to Bob. In particular, she wants to avoid that Eve is eavesdropping on the message. She cannot understand what she's sending. So we cannot send the message in plain. We have to do something different. Now, how do we use our public key encryption scheme? So again, what we do is if Alice wants to send a message to Bob, Bob has to do something first. Namely, Bob uses the key generation algorithm of our public key encryption scheme and generates public key and secret key. Don't worry, I sometimes switch these things. So PK, SK, or SK, PK, it's a little bit random. Anyway, but SK is always a secret key or private key, and PK is always a public key, so it shouldn't be confusing. So he generates such a key pair, keeps the secret key to himself, but publishes, say, the public key under his name in a so-called key database. So that's as in the signature setting. Then Alice, to send a message to Bob, retrieves Bob's public key. But obviously, if this is a public database, also the eavesdropper Eve can retrieve that public key. But Alice has a public key of Bob now, and what she does with the public key, she encrypts the message M with Bob's public key to obtain the ciphertext C, sends C over to Bob. And Bob, on the other hand, has a secret key, and by correctness required by the correctness requirement, he can now decrypt the message M by decrypt the ciphertext C to obtain the message M. So, but as in the digital signature case, Eve can also obtain the public key. So we have to take, as in the digital signature case, where we always assumed in our security games that the adversary gets a public key. Here we also need, in our security definitions, assume that adversaries get the public key. Only the secret key is private. Okay. As you can see, this picture here only allows, or this process only allows Alice to send a message to Bob. So if Bob wants to send a message to M, then Alice has to generate her own pair of public and secret key. And then Bob has to use Alice's public key to encrypt the message for Alice. So this is not a two-way technique. If we want to reverse the communication direction, Alice has to do what here Bob did. And that's why this often also is called asymmetric encryption, because you use for both directions, you use a different key pair, where the roles of Alice and Bob and the public and secret keys are reversed. As in this case of digital signatures, we also have to make sure that when Alice retrieves Bob's public key, that's really Bob's public key. And as I said before, we'll later briefly look at how to do this using certificates or actually digital signatures. But for the time being, we don't worry about that. So we assume always that if Alice thinks she has Bob's keys, she actually has Bob's key. Okay. Also, remember that from the case of digital signatures, we had a similar picture, but here the sender kept the secret, the sender of a message signed with a secret key, the receiver verified with a public key. So the syntax is quite different. And it's not just that you can reverse things to get public key encryption from digital signatures or vice versa. That's not true. But what's similar here to actually the same as in the digital signature case is that since the adversary gets the public key of Bob, all security definitions must include that we cannot compute efficiently the secret key from the public key. Because if we could, Eve getting the public key can easily then if she could compute the secret key from Bob, then there is no confidentiality at all. Okay? So everything in terms of security will imply that there can be no efficient algorithm that computes secret keys from public keys. Okay. So far, so good. I won't give you an example today because I will construct an example later. So I won't give you something that's insecure. Later on, we construct something that's secure. So then we need to discuss, of course, what do we mean by security? And so we define this again using security games. And here we first look at the eavesdropping security game. And you actually know this thing pretty much. It's very similar to what we've seen before, but with a slight twist. So we have our public key encryption scheme pi that we are looking at. And then we define an eavesdropping game between challenger C and A for this scheme pi as follows. On input 1 to the n, the challenger chooses a secret key public key pair using the key generation algorithm on input 1 to the n. And it gives PK to A because it's a public key encryption scheme, so adversaries should get the public key, but not the secret key. Then, given the public key, A computes two messages M0 and M1 with the same length. Assume for the time being that we're looking at the general case, so the scheme is defined on messages of arbitrary length. If it's a fixed length message, encryption scheme for messages of fixed length, then this is automatically satisfied, because otherwise one of the messages is not a legitimate message. Again, the same length because encryption schemes cannot hide the length of messages. So that's sort of one piece of information that they give away. Then, as before, C chooses a bit uniformly at random and encrypts the message NB. So it picks the two messages, one of the two messages uniformly at random, indicated by this B. And it sends C to A. Eventually, A does something and it outputs a bit B prime. And the result of the game is 1 if B is equal to B prime, and otherwise the result is 0. Okay, and I'll give you the formal definitions, the ones that you expect now in 2 slides. Okay? So this was the eavesdropping indistinguishability game. But in the case of private key encryption scheme, we also had this chosen plaintext indistinguishability game. So let's just generalize that to the public key setting. And here we get that we have again the common input 1 to the n. C generates the keys. It gives pk to A, and A asks for encryptions of the adaptively chosen plaintext and gets the corresponding ciphertext. Adaptively chosen. After having chosen P1, it can first wait for the answer from C, then depending on the encryption, it can pick P2 and so on. And eventually A outputs 2 messages as before, of the same length. B chooses the bit uniformly at random and it computes the corresponding the ciphertext of the corresponding message and sends C to A. A asks for more encryptions. A outputs a B prime. And the result of the game is 1 if and only if B is equal to B prime. Yeah. Good. Then we can do our usual stuff, right? Pub A pi eve n denotes the output of the eavesdropping game of the eavesdropping indistinguishable game on input 1 to the n. Peak pub k cpa a pi of n denotes the output of the chosen plaintext indistinguishability game on input 1 to the n. And then we define the eavesdropping advantage as the difference between the probability of this thing being 1 minus 1/2, because we can always win with probability 1/2 as an adversary. We can just pick a bit uniformly at random. And for the CPA advantage we have here, instead of the eavesdropping game, we look at the CPA game, where these probabilities here are over the complete probability, the random choices made in this game. Now, what are the random choices made in this game? We have random choices here, because this is a probabilistic algorithm. We have random choices here because A is a probabilistic algorithm. So it's over the random choices of A as well. Each of the encryptions uses the probabilistic encryption algorithm. So it's over these random choices as well. Okay? And so random choices of A, random choices of the encryption algorithm, random choices of the key generation algorithm. The random choice made here. The random choices obviously made here. The random choices, again, made by A here. The random choices, and that's it. So all the random choices made by the key generation algorithm, the encryption algorithm, the use of the encryption algorithm, the use of A itself, of the adversary, and obviously over the bit B. Okay? Over all these random choices, this is what we use here in the probability here. Question?
And don't both schemes use the same security?
That's what I was just asking. What it's the next thing? What's funny about this game here? Yeah.
Actually, A can compute the encryption on its own because it is public key.
Yeah. We don't need this oracle for the encryptions. Yeah. Because it gets the key, public key anyway. Public key. So it doesn't need, there is no need for these encryption groups. Okay. So that's what we have here. Then we have these definitions, the eavesdropping, it's eavesdropping secure if this is negligible, and it's CPA secure if the CPA advantage is negligible. And then we have the observation that for public key encryption schemes, the two things are the same. Eavesdropping is the same as CPA. So it's if and only if. So for public key encryption scheme, we don't need to provide chosen plaintext attacks are eavesdropping attacks. Such this way. So and we only talk about CPA security, but use the eavesdropping game. So that nobody says eavesdropping security for public key encryption scheme at all. But always they use CPA, but the way obviously they define CPA is using this here. So they would call this here the CPA indistinguishability game. And I follow that. So I talk about CPA security. Sometimes I say eavesdropping security, but never mind. But it's always, I always mean chosen plaintext security, but I talk about this game. Later on, I will also talk about CCA security, security against chosen ciphertext attacks. Then it makes sense to talk about oracle, decryption oracles, because the adversary is only given the public key, not the secret key. For a secure encryption scheme, the adversary should not be able to compute the secret key from the public key on its own. So that's a huge difference. Okay. So this is our stuff here. Okay. Now this has some important and nice consequences. Remember that we also talked about, in the context of private key encryption schemes, we talked about the multiple security for multiple encryptions. Okay? That becomes important when we, and that's how we used it there, when we have, and that's typically the case, we first have an encryption scheme for messages of some fixed length. And then we want to extend that to messages of arbitrary length. And what we do there, in one way or another, is we simply chop up our long message into blocks of the required length for our original scheme for messages of some fixed length, and then apply these things separately to these things. That would be the ECB mode. We saw also that we had this more complicated way of randomized counter mode and stuff like that, which was much better. But as we saw in the private key setting, eavesdropping security did not imply necessarily security for multiple encryption. That was a strong indication that eavesdropping security was not really a good security notion. So let's do the same stuff here and see what we get in the public key setting. So first, let's define the security for multiple encryptions, or indistinguishability for multiple encryptions. Again, for a public key encryption scheme pi, the multiple messages indistinguishability game between challenger C and an adversary A is defined as follows. I denoted with this mult here as a superscript. On a common input 1 to the n, C chooses as before the key pair, gives a public key pk to A. Then A outputs two vectors of messages, M01 up to M0T, M11 up to M1T, of messages where at least at each position the messages have the same length. Okay, if it's in private key encryption scheme for messages of fixed length, that's given anyway. Okay. Then C chooses a bit 01 and computes the encryption of all messages either in this sequence or in this sequence. It's always the MBI. So the B is fixed, it's either 0 or 1. So either all messages here or all messages here. And then it sends over the sequence of the ciphertext, so the ciphertext for M0, capital M0, capital M1, to A. A outputs a bit B prime. And the result of the game is B is 1, if B is equal to B prime, otherwise the result is 0. Okay, and then we have our usual stuff. Pub k mult a pi of n denotes the result of the multiple messages in this indistinguishability game. We have our advantage in the eavesdropping multiple game. And we say that has multiple indistinguishable, I has multiple indistinguishable encryption under chosen plaintext attacks if for every PPT algorithm A there is a negligible function such that this eavesdropping advantage. And here I wrote eaves in front. I could have also written CPA, it doesn't matter. Multiple is mu of n. So sometimes I usually write here just eaves, although I talk about the CPA stuff. Don't worry about it. It's all the same anyway. Yeah. Okay. And we saw that in the private key setting, for eavesdropping security, indistinguishable encryptions does not necessarily imply the multiple indistinguishable encryption. Okay. And the reason was that private key encryption in the eavesdropping setting, you can achieve eavesdropping security by deterministic scheme, deterministic encryptions. And deterministic encryptions cannot have multiple indistinguishable encryptions. That simply doesn't work. Okay. But we also saw that CPA security can also not be achieved by deterministic encryptions. Now, in the public key setting, eavesdropping and CPA are the same. You can easily see, obviously, that in this game, you cannot achieve this security for eavesdropping for deterministic encryption algorithms because A gets a public key itself. So it can compute, in particular, it can compute encryptions of M0 and M1. Right? So if that was deterministic, no way that this could lead to something that's secure in that setting. Right? Because well, if it's deterministic, just recompute it. You can do it yourself. So in the public key setting, we cannot have, for any kind of security definition, we cannot have that the encryption algorithm of an encryption scheme is deterministic. That cannot lead to eavesdropping security, CPA security. So from the very beginning, we need to have probabilistic encryption. We need to have immediately it's CPA security as well, and hence probabilistic stuff. And that's why maybe the following. And I said that in the private key setting, I stated the theorem that says that if a private key encryption scheme is CPA secure, then it has also multiple indistinguishable encryptions. And the same is true for public key encryption schemes. So this is our important theorem 10.6. A public key encryption scheme pi has indistinguishable encryptions under chosen plaintext attacks if and only if it has multiple indistinguishable encryptions under chosen plaintext attacks. So this is the same as in the private key setting. But this time I will prove it. And then you will prove this theorem in the private key setting yourself. It's actually a slight modification. And as it turns out, this is not just for practical reasons that I just said, but it's really important for our construction of CPA secure public key encryption schemes. The reason is that my first construction for a CPA secure public key encryption scheme will only be able to encrypt single bits. That's not a lot, right? And people usually don't want to encrypt single bits. Sometimes it makes sense in some applications, but usually you want to do something more complicated. But this says, good, if I can encrypt single bits, I can encrypt as many bits as I like securely. Just encrypt them individually using the same public key. That works. May not be very efficient, but it works. At least as security goes. Yeah. So what I want to do is I want to prove this theorem 10.6. And in the proof, we use one of the most important techniques in modern cryptography, namely the hybrid technique. That's in one way or another used in almost any security proof today for something that's moderately complex. And I will explain it in detail. So this is what we do. But to not make our lives too difficult, I will prove it only for the case that t is equal to 2. But that actually is like the general case, but it makes things easier to explain. It makes things, I can just write down things explicitly. In the lecture notes, you see the general proof. Here I will give you just the proof for t equal 2, and I'll just then indicate how you generalize that. Okay. So we use a hybrid argument. Okay. So let we start as usual. Let A be fixed. Arbitrary adversary in this game here. And I so from A construct A prime in. So I use the eavesdropping variant, so no queries need against the same. And by epsilon n, I denote the eavesdropping advantage of A this way. Yeah. The eavesdropping advantage multiple game of A pi of n, which is so the probability that up A mod A comma pi of n is 1. Delta n is CPA advantage of A pi of n, which is the probability of up Okay, and I use obviously the eavesdropping game because I don't need anything else. This should be fine. Yep. And you may remember this discussion that we had that these absolute values are annoying. And sometimes we don't like them. In this case, it doesn't even really matter, but let's drop them anyway. So in some cases during the proofs, I will just drop them. Okay. Okay. Now let's first look at this A prime on the slides. Okay. And so here it is. And remember, I only talk about the case where t is equal to 2. In general, this t is a function of n and it has polynomially many things. Okay. So let pi be our public key encryption scheme under consideration. We use this adversary A that I define that's fixed but arbitrary, and then we have this A prime as follows. So it gets as input 1 to the n and pk, right? Because we are now in the we talk about A prime, we talk about this game here, anything, and here it gets to the real game. In this game, we give it pk as well. So we have to explain what does A here in this step, and we have to explain what A does in this step. So that's what I'm trying to explain here. So, and here we are. So it simulates A with input 1 to the n and pk to obtain two vectors of messages M0, capital M0, which is M01, M02, and M1, which is M11, M12. Where the messages in the corresponding positions have the same length. So it starts A in the multiple messages game in step 2 after A has received this public key. But the public key here for A prime is generated using the key generation algorithm. So A gets really the public key as expected in its game, in its security game. Now A prime chooses an I uniformly at random from 1 to 2. So it picks a position, either this one or this one. And then it returns, remember, A prime is on single messages. It's for single messages from our space. So, and then it returns M0, I, M1, I to C. Okay, to its challenger. So it picks a position here, and then it gives the message from M0 in that position and in M1 from that position. That's the way A prime chooses it two messages to give to its challenger. Not sequences of messages, but one message. Then, upon receiving the ciphertext from C, so now A, which is in the eavesdropping game, it receives, say, I call this CI, C index I, for MBI from C, where I is either 1 or 2. I do the following. For J is less than I I choose Cj to be the encryption of M0J. I'll explain this later in concrete terms. And for j is larger than I choose Cj to be MPK, the encryption under PK of M1J. And I simulate A with challenge ciphertext C1, C2. And I output the bit B prime that A outputs. Okay. So let's see what we get here. Okay. Let's look at what kind of ciphertext we generate here. Okay. So let's make a little table. Okay, let's say if we pick I to be 1, or let's say I is 2, I is 1, B is 0, B is 1. Okay. Probably need a little bit more space here. Okay. So, okay, when I is 2, I pick here M and B is 0. The thing that I pick here is M02, right? And there is a J, index J, that is less than 2, namely 1. Okay, there's just one that's below that. So, and then I pick C1 to be the encryption of M01. Okay. So what I get here is the encryption under PK of M01 combined with the encryption under PK of M02. Which is the encryption of this M0, the capital M0. Now let's look at the case that B is equal to 1. Now B is equal to 1, but I is still 2. I get at the second position, I get M12, the encryption of M12. In the first position, I still get M01, because that's determined by the position 1 alone. So here, I get the encryption under PK of M01 combined with the encryption of M12. So this is not anything that A would get normally in its game, because in its game it gets either the encryption of this thing completely or this thing completely. Here I generate something that's in between. It's called a hybrid. Okay. Now let's look at the case I is 1. And the two things that we have, so I is 1, and B is 0. So B0, the first thing that I get is M01. So the first ciphertext, this guy here, C1, is the encryption of M01. But J less than 1 means J is 0, that doesn't exist. So we are immediately in this case, namely for J is 2. And for J is 2, I encrypt M12. So here I get so the same thing that I get here. And if it's B is equal to 1 and I is equal to 1, I get here M11, and I get still here M12. So I get here the encryption PK M11 and the encryption under the PK of M12. Okay, and this is the encryption of this thing here. Okay. If there is more than J is not equal to 2, what you get is always a prefix where you all encrypt the messages from M0 and the suffix where you encrypt the messages from M1. That's a mixture. It's a hybrid. So, and what we do is we call these things then, and then we define the hybrid distributions on ciphertext. Okay, because all these things here, all these things are random variables, right? Because, well, in the key generation algorithm, there is randomness in the choice of A, M0, capital M0, M1 is randomness. Choice of I is randomness, and the choice of B is randomness, and the choice of the encryption is randomness. So these are all not fixed values. These are all kind of distributions. And these are the distributions that I'll define here. So I have 3 different distributions. You see that these two are the same here on sequences of ciphertext by the following process. So it's a distribution that I define by a process that outputs things, and the process is a random process. So the first step of the process, I generate the keys. The second step of the process is I run A on input. Oops, I should run A only on input PK. Sorry, this is not correct. To obtain the 2 sequences of messages. Right? And then I have for k is equal to 2, I return this M01, M02. So this is this guy here. Okay. This N refers to this here. The K has a meaning. The K is the last index where I put in this sequence an encryption of a message from capital M0. And that's also true in the general case. So, and before that position, everything is from M0. After that position, everything is from M1. And in that position, this determines the position where this switch occurs. So K is equal to 2, everything from M0. K is equal to 1, everything from M1. So the last position where I put in something from M0 is a zeros position, which doesn't exist because I only have positions 1, 2. And for K is equal to 1, I have this mixed one. So 1 is the last position where I put in something from M0, from capital M0. So it's M01 and M12. So this here is H and 2. This here is H and 1. This here is H and 0. And this is again H and 1. Okay. So I have these hybrids. And I forgot something to do. Crypt. I was supposed to do that today, I think.
Somebody's not balance.
Exactly. So yeah, that's true. Okay. So just okay, forget that. So what's now the idea behind the proof? And why did I introduce these hybrids? Now, the problem is when I want to look at relate this sort of to my original eavesdropping game, I have like these two things, two positions at which this and this differs. Okay. But if you now look at this thing here, this and this, they differ only in one position, namely here. Okay. So, and the idea is if I can distinguish whether I get something from this hybrid or from this hybrid, I should be able to distinguish whether I get an encryption of M11 or of encryption of M01, which is exactly my eavesdropping game for single messages. If I get this and this, if I can distinguish between these two distributions, again, they differ only in one position, namely in the second one. But then again, I should be able to use that distinguisher or that algorithm to distinguish between encryptions here and here. So by introducing this hybrid now, and then if now I will argue that this cannot be these two things, this and this or this and this, you cannot distinguish as an adversary, because if you did, you would break the eavesdropping security of my scheme because it's just one position. Okay. So this and this are indistinguishable. This and this are indistinguishable. But if two things are indistinguishable via some intermediary, then these two things should also be indistinguishable. No? If yellow is indistinguishable from green and green is indistinguishable from red, then what did I start with? Yellow is indistinguishable from red or whatever. Okay? And we could do that directly this way, use just triangle inequality. Turns out we can a little bit be a little bit more precise. But that's the idea. By introducing this hybrid, I introduced distributions on ciphertext that only, on sequences of ciphertext that only differ in one position. And because they differ in that one position, I can use that to get an adversary in my original game. And that's exactly basically what we do. Okay. And these are the hybrids. Okay, in the actual process using here, I'll do it a little bit differently. The analysis is a little bit different. But you can always think like you do these hybrids and then you say, well, I have these two things that I'm interested in, and I have this one thing in the middle that is like a mediary between the two things. And if you have longer sequences, you do more intermediaries in between to get from one to the other. Okay, so how do we analyze this now in detail? And here you see what I wrote down on the board. You see it here. It's exactly the same sequence, right? Or the same ordering. Yeah, just that I wrote down this with the HN I's and HN case. Okay, now let's go back to our stuff, to our proof. I will erase this. It's on the thing anyway. Okay. Okay, we need to analyze this epsilon or delta n, right? So let's do this delta n, which hopefully I define the CPA advantage of A prime against pi of n, which is, and let me try it with the absolute values. It doesn't really, it works. So this is the probability of the probability of pop k eavesdropping A prime against pi of n is 1 minus 1/2 in absolute value. Okay? Okay. So when does this guy win? Well, let's do something very simple at the very beginning. This is, well, the probability that A prime outputs 0 and B was 0 plus the probability that A prime outputs 1 and B was 1. Right? This is just rewriting this. So it's the probability A prime outputs 0 and B is equal to 0 plus, this obviously is a disjoint, these are disjoint events, right? The probability A prime outputs 1 and, sorry that my 1s and my n's are so hard to distinguish, and B is 1 minus 1/2 in absolute value. Right? Okay. So let's just look at this probability here first. Okay? The probability that B outputs 0 and B is 1. So this guy here, so the probability A prime outputs 0 and B is 0. This is the same as the probability A prime outputs 0 and B is 0 and I is 2 plus the probability that A prime outputs 0 and B is 0 and I is 1. It picks one of them and it can be that the IH or I also include this I is 1. Okay? Good. Then by conditional probabilities, this is the same as the probability that A prime outputs 0 conditioned on B is 0 and I is equal to 2 times the probability that, now let me just see what I wrote here. Okay. Sorry. Okay, let me just rewrite this a little bit because otherwise I get in trouble. So from here, let's replace this by condition, and then I put a 1/2 in front of the whole thing. Okay, I do the same here, condition, and I should not put a 1 in front of it. Well, I can put also here 1/2 because I condition on b being 1, but here I have a minus 1/2. I can replace that by -1 and put the 1/2 completely in front of the whole thing. And then I want to do this here. This, and I want to do slightly differently. And I want this here as well. This way. Okay. And then I can do this the same as I is 2 conditioned on b is 0 plus the probability a prime outputs 0 condition b is 0 and I is 1 times the probability I is 1 condition b is 0. I just sort of put this into condition as well, and then I just also condition obviously on this. Just conditional probabilities, the usual stuff. Okay, but what we can see is that the choice of I is independent of the choice of B. Right? And we have for I just 2 choices, so this is 1/2. And this is also 1. Now let's rewrite this in terms of our distributions. Right? Now I condition on I 0, B being 0, I being 2. So the things, the C, the ciphertext that A gets in this step here, in this step, it gets a ciphertext distributed according to H and 2. In this case, it gets a ciphertext distributed according to H and 1. Right? So I can rewrite this in the following way. So this is the same as the probability. The ciphertext is distributed according to H and 2. A on input, C outputs 0. And I should put a 1/2 in front of it. Plus 1/2 the probability over C being distributed according to H and 1 A on input, C output 0. Also, and that is actually the same proof, just I start out with output 0, outputs 1, and B is equal to 1. And then do the same sequence of steps, basically. There I get that the probability A prime outputs 1 conditioned on B being 1 is 1/2 the probability over C according to H and 0. AC outputs 1 plus 1/2 of the probability C to H and 1. AC outputs 1. Okay. So the nice thing now is H and 2, H and 0 appear once here. And here they appear, H and 1 appears here and here in both things. And yeah. So, and you can see that here is C according to H and 1, AC output 0, C output according to H and 1, AC outputs 1. But A outputs either 0 or 1. So the two events sum up to 1, two probabilities. Okay, so they will kind of disappear nicely. Okay. So this is a magic, like where the proof comes a little bit more detailed than just doing this triangle inequality. Okay, good. So now let's put everything together. So now I plug these two things, this and this, into this. Okay. See what we get. I'd rather, okay, let me do this step by step so that I don't get wrong. Hopefully I won't get confused. Okay, let's try it. Yeah, okay, let's try. So this here is the 1/2 states. This here was the probability CH and 2 AC output 0 plus, I forgot it 1/2, right? 1/2. I forgot this 1/2 of 1 to 8. Yeah. Forgot this 1/2 in front of it. So this is 1/2 probability AC. So C distributed H and 2. AC is 0 plus 1/2 probability C according to H and 1. AC is 0 plus 1/2 probability C H and 1. A C is 1 plus 1/2 probability H of C distributed according to H and 0. A of C is 1 minus this one. Okay. Good. So this together with this gives 1. So forget about the 1/2. Probability that it outputs 1. Probability that it sorry, this and this, these two together. The two probabilities together are 1 because A outputs either 0 or 1. So this whole thing here is 1/2. We keep this here. Minus this together, these two together give 1. We multiply them both with 1/2. So we have a plus 1/2, so a minus 1/2 here. Okay. You still have this minus 1, but these two probabilities sum up to 1, but they are both multiplied with 1/2. 1/2 minus 1 is minus 1/2. Okay.
The 1/2 before the absolute value must go away.
No, it stays. I want that. And that's correct because it's still in here. I didn't do anything with this 1/2. I just collected these two things to give me 1/2. But I still have this minus 1/2, so plus 1/2 minus 1/2 is minus 1/2.
Yeah, but there's still 1/2 to.
Yeah, which I had here as well.
Yeah, but
and here I got these here. Here I got 1/2 because these 1/2 that I get in addition to here is over the choices of i's. They are there. They're still there. I simply copied things and didn't do anything. So really interesting. Yeah. But what we get here now is these two probabilities with 1/2 in front, these two terms here, is really the probability that A wins its game. If you go away here to them, you will see that something like this here, what I did with condition on, do this whole thing with A, condition on B being 0, blah, blah, blah. And you get exactly these two probabilities here, this 1/2 plus the 1/2 this here is really the probability that A wins its game. Okay. Let me do this maybe. Yeah. Yes. Okay, let's do that. Good. And I keep, I'll erase this here because this was the 1/2 I wanted. They are correct. And I really want them on the board because I explained the general case. These 1/2 will go away and replaced by something else. Okay, let's look at the probability that in the public key game and A is eavesdropping, A, pi of N is 1. Okay, this is the probability that A outputs 0 and B is 0 plus the probability that A outputs 1 and B is 1, right? Which is one half the probability A outputs 0, condition B is 0, plus one half the probability A outputs 1, conditioned on B being 1. Okay? But in the game, right, we're now talking about this game here, at the very, very beginning, this one here. If B is 0, then A gets a ciphertext that's distributed according to HN2 by our definition. Both come from M0. And with B is 1, both come from M1. So this is really the probability 1/2 times the probability of A C according to HN2. A on C is 0 plus 1/2 the probability H C according to HN0. A of C is 1. Okay. So this here really is this probability. And you see that I need those 1/2 in there. So this here really is now do various steps combined. This is 1/2. This is this 1/2 that I keep. Here, I replace this by this guy here, minus 1/2. This is really the advantage of A in its eavesdropping game, which we denoted by epsilon n. Okay. So epsilon n and delta n are related by this factor of 1/2. If one is negligible, then the other is negligible as well. And we are done. And you see that I really need this 1/2 because it comes from here. In the general proof, sums become much larger. There's more than one hybrid. They sort of add up nicely, cancel, they add up nicely. The thing that's different is that this guy here, this 1/2 becomes a 1 over T of n. So this becomes from the i's. This comes really from this relation here. This 1/2 that I have in front of you comes from this relation here. Okay, but this here, this was from the i's. This becomes a 1 over T of n. So in the general case, 1 of epsilon n and delta n are related by this factor of T of n. And that's why we need that in this multiple encryption game, in the definition in this game, T of n must be polynomial. If you get super polynomially many encryptions, there's no hope that you get to a multiple encryption security if you get too many things. Okay, so T must be polynomial for that to be true. But the nice thing here, I could have done that with triangle inequality, but then I would have gotten an inequality sign. This shows that it's really equality. You cannot avoid this factor of 2. But intuitively, it's always good to remember this thing here. This is indistinguishable because they differ only in one position, and that relates to the original eavesdropping game. These two indistinguishable because they differ in only one position. So these two must also be indistinguishable. And you can do that. So if you relate these two, not just by one intermediary, we can do that with many intermediaries where two consecutive intermediaries only differ in one position. Okay? That's the hybrid. They only differ in one position. Okay, so, and you probably now see why I don't want to do the general proof on the board. It doesn't add anything, really. There's nothing that I need to add. I just have to write out more complicated. Okay, so that is good to know. We have this multiple security against multiple indistinguishable ability of multiple encryptions. And we saw this extremely important technique of hybrid distributions. It's related to game hopping, but it's kind of a simplified version of game hopping. And game hopping, it is really so simplified that you won't recognize necessarily that they are the same. Right? Because from one game to the other in the hybrid, you don't use an additional security assumption. You just do the math, period. So, and it's we'll see it in the when we look at surprisingly, not surprisingly, when we look at hybrid encryptions, we do a hybrid argument to prove it. It seems like a natural idea to do, right? But again, it's such an important technique and such a well-known technique that people don't mention it when they apply it. They just say easy to see, standard argument. Um, you can spend weeks thinking about it, but it's then hybrid argument. Okay. If they are nice, they tell you it's a hybrid argument. Just buy a hybrid argument. Okay, good. So that is for the first part of today's lecture. In the second part, we actually construct a public key encryption scheme. But we'll construct it from the message space 0, 1. As I said, that's not really such an exciting thing, but given our theorem 10.6, once we have it for 0, 1, we have it actually for 0, n, 0, 1 star. If you want to encrypt long messages, you must make sure that your key is chosen with the right security parameter, because T of n, and must be polynomial in n. So then if you have a certain length, you must make sure that this polynomial is good enough. Otherwise, you lose a lot in security. Okay, good. So let's do a break for until 10 o'clock. Okay. Good. Okay, see you then. And as I said, we do that using so-called trapdoor permutations. And we first want to achieve CPA security. One example for trapdoor is RSA. So RSA, we are not going to use it as an encryption scheme itself, which as such it's not secure. It would be deterministic in the textbook version, but we may use it as a trapdoor permutation. And from trapdoor permutations, we obtain CPA public key, secure CPA public key encryption messages of length 1. And then we apply theorem 10.6 and we're done. So we just want to encrypt one bit. We'll see where in the proof it becomes important that it's a single bit. It's a little bit technical, but it's clear where we actually use it. So first, we need to define function families. I mean, when we talk about public key encryption schemes, we always talk about public keys. We need to index things with certain things, and so the setting in which this is best discussed is the notion of function families. And then we'll give RSA as an example for function family. So function family is a triple of 3 algorithms: key gen, a sampling algorithm, and an evaluation algorithm, F. The key generation algorithm, and this is not, again, it's syntactic. It doesn't say about anything about what kind of security properties it may have. That comes later. So the key generation algorithm on input 1 to the n plays later the role of security parameter, outputs a description of parameters, certain parameters. Outputs, and we'll see the example. But the description length should be at least n. So the description length, we can everything describe in terms of bits. The number of bits should be long enough or large enough. And each of these parameters I defines a finite domain di and a finite range ri for a function fi going from di to r. So the description that gen outputs defines basically a function, including everything. Right? The domain and the function itself will be defined later. The sampling on input 1 to the n parameters I chooses an element uniformly at random from di. So that's just, we know how to generate elements uniformly at random from finite sets, so that's the way the sampling algorithm does that. F is a deterministic algorithm. Input 1 to the n, I, and an x in di. And then this algorithm F outputs an element y from Ri. And this is denoted by Fi of x. Okay, so since F is deterministic, if we fix this I, then this F, the algorithm, defines really a function from di to R. Because it's deterministic. For every x in di, it outputs a y in Ri. That's the image. A particular case is a special case if when for all i's parameter sets, we have that di is equal to Ri and the function di is a permutation. Then we call pi a family of permutations. Let's maybe look at, the RSA family of permutations as an example. And forget about trapdoors and stuff like that. Forget about this part here. We just look at it as RSA as a function family. And gen be an arbitrary RSA generator. Remember, an oscillator is an algorithm that generates RSA keys. So the product of primes P, the primes P, Q, the product N, P, and the D. Forget about the D for a while. So in this case, the description parameters I for RSA consists of the public key, of RSA, which is N and E. We don't even need the P and Q for the parameters. Right? And then, so this is here. And in the sampling algorithm, it outputs an element from Zn. This is the domain of the function that we use. The function itself, given by f, it simply output x to the e mod n. So the description parameters are n comma e. The sampling simply outputs its required uniformly random, and f simply computes the e power mod n of the argument x. And this is not just a function family, it's really a permutation, a family of permutations, because we have seen that this powering with E is a permutation. We even gave explicitly the inverse, namely powering with D, where D is the corresponding secret key. Okay? So that would be a family of functions. And that's the right setting for everything we do in basically public cryptography, public key cryptography. Okay? Yeah? Clear as an example? So the parameters are some numbers that define something, typically, or group elements, or define a group, or whatever. Yeah. Now, remember that we had this notion of one-way functions. And when I talked about one-way functions, I said, well, there's always a problem because we have to do all these, we have to restrict the domain, have to have special domains. Here, we have the same problems and we want to deal with them more formally, but also we want to define trapdoors. And for trapdoors, we really need this setting where we have functions defined by these parameters and similar things. Okay? But for that, I want to generalize this notion of one-wayness to function families. Recall that a one-way function is a function that's easy to evaluate but hard to invert. Right? Now we want to do something similar, define something similar here. And to do that, to define one-way functions and to say that it's hard to invert the function, we have to define this inverting game. So we generalize our inverting game to the case of function families. And this is done as follows. So we have now a function family pi, and the inverting game pi for pi and anniversary A is defined as follows. First, we use on input n. With the T generation algorithm is used, or the parameter generation algorithm is used to compute the parameters I. Then we use the sampling algorithm with input I to get an x. And then we set y to be fr of x. And we give A the input 1 to the n, I, and y. And it's asked to output an x prime. And it wins the result of the game is 1 if and only if fi of x prime is equal to 1. Recall that in the one definition inverting game for one-way function, we had a similar thing here where we made sure that there is a pre-image of y by actually picking also an x from 0, 1, n, and then setting y to be f of x, and this is all similar. So the only difference is that here we first pick these parameters that define the function. And we write invert a pi of n is 1 if the output is 1. And then we say that A has won or succeeded. And the inverting advantage is simply the probability that it outputs 1. The probability being over the random choices here, the random choices here, the random choices here. Also the ones that are used by A. Okay. And we go to, okay, and we say that this family is a one-way function family, or simply one way for every probabilistic polynomial time A. There is a negligible function mu such that for all n in n, this inverting advantage is negligible. And if pi is in addition permutation, then we call it a one-way family of permutations. And also remember or recall that if we have a function family that's a permutation, this step here is not necessary. We could just pick y uniformly using the sampling algorithm. Because it's a permutation, you sample uniformly, apply a permutation, well, it's uniform. Y is uniform as well. So there would be no need to do that. But okay. And okay. If you, and I will talk about this in detail a little bit later, if you remember, we had that we talked about RSA generators and good or bad RSA generators, or that RSA is hard relative to a certain generator. And if a certain RSA problem, the inverting problem, is hard relative to the generator, then this is exactly the one-wayness of RSA with respect to that generator. Okay? But then we have to make sure that we generate these things sort of in such a way that we don't generate dangerous, easy stuff. Okay? So this here doesn't imply that for all parameters, this function fi is hard to invert. It simply implies that those i's for which this is fi is not hard to invert, they are not get picked with significant probability. That's one of the consequences. Okay, and that was also reflected in this RSA generator stuff. Okay, and finally now we can find this extremely important notion of trapdoor permutations. So trapdoor permutation is a quadruple of algorithms now, gen, sum, f, invert of probabilistic polynomial time algorithms, such that the key generation algorithm on input 1 to the n outputs the descriptions of two sets of parameters. I set the size of the instances, or description size of the instance should be at least n. And the first component of a pair ITD defines a finite set DI. Talk about permutations, so there will be no error. And if we denote by gen 1, the algorithm obtained from gen by restricting its outputs to the first component I. We ignore this here. Then we require that this gen 1 sum f is a one-way family of permutations. Okay. So if I just give you the description parameters, then it's hard to invert. But that is the last component. Inverse is a deterministic algorithm, and on input 1 at the end, the trapdoor, y in di and an element x. It outputs an element x in, so this should be di, not I, di, such that the fi of f, if it gets fi of x as input together with the trapdoor, then it returns x for all x and di and all pairs of instance parameters and trapdoors. And I'm talking here about permutations. So if I give it fi of x, there is just one preimage that maps to this fi of x, namely x itself, because we're talking about permutations. Okay. So what this says is the function family, if I just give you the description parameters, it's hard to invert. But once I give you the trapdoor, you can invert. Okay. And an example of a trapdoor, the RS family of trapdoor permutations is RSA. Here we have a RSA key generator. The instance parameters are the public key that the RSA generator creates. The trapdoor is a secret key. The sampling, as I explained before, done uniformly at random on Zn. F is simply x to the e. Fi of x is simply x to the e. And the inverse is simply y to the d, not n. We saw that really inverts the whole thing. And what we have is that if the RSA problem is hard relative to gen, then this is a trapdoor permutation. Because, as I said, if the RSA problem is hard relative to gen, then this property here is satisfied. And this here is satisfied anyway, as we saw already. That's a simple mathematical problem. We have an inversion algorithm. That's a requirement. We assume for this RSA generator. Okay. So, okay, so these are trapdoor permutations. They are the main building block for public key encryption schemes and many variants of that. Do they exist? Well, we hope that they exist. Many people think that RSA generators that are hard, for which RSA problem is hard, exist, but there are many other candidates. But assuming that trapdoor permutations exist seems to be a stronger assumption than just the existence of one-way functions. We cannot show that if one-way functions exist, then trapdoor permutations exist. And there are results that indicate that this is really a stronger assumption. What that really means, there are complexity theory, there are relativized models of computations in which one-way functions exist, but no trapdoor permutations exist. But we hope that in our world, the state of affairs is that one-way functions exist and trapdoor permutations exist. Okay, so if you want to do public key encryption scheme, the first idea, if you have trapdoor permutations, is, well, this is my key generation algorithm, encryption, this is a public key, this is secret key as an RSA. The F provides me with the encryption, and this here provides me with the decryption. Except that cannot work. Because inf and f are deterministic. And we're talking about CPA security here. There is no deterministic CPA secure encryption scheme, neither in the public key nor in the private key setting. So we need to do something different. And the way we do that is using so-called hardcore predicates. Hardcore predicates, I skipped that part in the lecture, but if you go to the lecture notes, you will see that hardcore predicates are used to define pseudo-random generators. From pseudo-random generators, you get pseudo-random functions, and then you have private key encryption schemes. In the public key setting, we use also hardcore predicates, but we use them directly to encrypt, to design encryption schemes. So what is a hardcore predicate? a hardcore predicate is defined as follows. We look at a function family, gen sum f, which could also be a trapdoor permutation, family of trapdoor permutations, where we just restrict the key generation algorithm. Let HC be a deterministic algorithm that for all n in n, all instance parameters, and all x in di outputs a bit, a single bit. Okay? And this is denoted by HCI of x. The predicate, as you in computer science, any function that goes from some domain to bits is a predicate. 0 saying you don't have the predicate, 1 saying you have it. And we call HC a hardcore predicate for pi if for every probabilistic polynomial time algorithm there's a negligible function such that this advantage is negligible. What does this mean? So A gets as input I and Fi of x. X picked with the sampling algorithm and so on. And it predicts HC of I. This probability minus 1/2 is. So what does that mean? A does not get x itself. It only gets the image of x under my function Fi. But it has to predict the hardcore value, hardcore bit of x itself. Okay. So I give you the image, but you have to predict the hardcore predicate on the pre-image. So in the RSA setting, I give you x to the e, but you have to predict some predicate on x. Okay. Here's an example. So first of all, we can show that if trapdoor permutations exist, then trapdoor permutations with hardcore predicates exist. It's standard construction. For any RSA generator, the least significant bit is a hardcore predicate for the RSA function. And I want to tell you how can we show something like that. Give you a brief intuition or brief outline how you would prove something like that. So RSA, you get y, which is x to the e mod n. Okay. Now here you have x. And assume these are the bits of x. Okay. So bits of x. And say here most significant bit, here least significant bit. Now, what I show you is that to prove this theorem, I have to give you an algorithm that given y predicts the least significant of x, I can use to compute x entirely. If I just be able from y to compute the least significant bit, I need to give you an algorithm that computes all of x. Because then an algorithm then predicts or computes the least significant bit cannot exist under the assumption that RSA is hard to invert. Okay? Yeah? So the way you can view this is hardcore predicate as a lens that gives you this bit here. So this is a hardcore bit, HC, in the RSA case. Now assume for simplicity, my algorithm to predict the hardcore predicate works with probability 1. It always succeeds, not just with probability significant above 1/2. Assume it works with 1. Then I can first compute this bit here. Then if the bit is 1, I subtract that value from something. And then I can sort of move the lens to here. Right? So then this bit here is the least significant bit of 1/2 x, or 1/2 x minus x0 minus LSB of x. Right? I need this LSB subtracted to make this divisible by 2. So, yeah. But given that here, so if that is my new x, I'll say this is x bar, then I know that x bar to the e is given by, well, 1/2 to the x to the e, which is 1 to the minus e times x to the e, which is 1 to the minus e times y mod n. Right? So I can compute this value. Right? Given all the information I have this y, and this guy here, 2 to the minus e, I have e. It's part of the instance parameters, so I can compute it myself. And then I compute the least significant bit of x bar. One does I have the least significant bits of x bar. I subtract the least significant bit, divide by 2, multiply by 2 to the minus e, get the next bit. So I can move this lens over this complete sort of hidden x, but I can always peek in and see the individual bits. That picture simplifies a lot of stuff because my algorithm does not get the least significant bit with probability 1, only with 1/2 plus something that's significant. Well, I'll repeat the argument and it can boost that probability to close to 1. This here, you have to be a little bit careful because it's not dividing by 2, but multiplying, and there's some little technical problems here, but anyway, so it works. And that's how you show that this theorem, particularly you show if this was not a hardcore predicate, you could actually invert the RSA function relative to your generator. Now we want to have a construction that starts out with a arbitrary trapdoor permutation, family of trapdoor permutations, and a hardcore predicate for that, and defines a public key encryption scheme that works only on bits, individual bits. So we have our trapdoor permutation pi bar. Gen bar is a key generation of the generation algorithm sampling F inverting. So that's a trapdoor permutation. That it's family of permutations. And let HC be a hardcore predicate for pi bar. Actually, hardcore predicates only exist for trapdoor permutations because otherwise you can invert. Then define a public key encryption scheme pi with message length 1, spaces 0, 1, as follows. The key generation algorithm on 1 to the n chooses the INTD given using this the generation algorithm for the family, and sets the secret key to be T-day and the public key to be I. So in RSA, I would be n comma e, and sk would be n comma d. So really what the outline that I did is for the key generation RSA is correct. and on input 1 to the n public key I, and a message m in 0, 1. It chooses x from the sampling algorithm, using the sampling algorithm with I, and outputs a ciphertext consisting of fi of x and nx or hci of x. HCI of x, not fi of x. Okay? And the decryption algorithm on input sk 1 to the n, and the sk, which is the trapdoor, and the ciphertext, which consists of y and s, and di x or 0, 1. This is a bit. Compute b to b. Well, what I do? I do the obvious thing, right? I first invert this guy here, which I can because I have the trapdoor. And because it's a permutation, it gives me my original x back, not some other preimage. It must be x. And then I evaluate the hardcore predicate on this value here, the invert, and get back the message S as mx or b. So you see, this really requires this to be a permutation, because it doesn't help me if I get here some other preimage that may have a different hardcore predicate. I really need that one. That's why I need a permutation. And that's a construction. It's a wasteful construction, right? Because to encrypt a single bit, you have a ciphertext that consists of a bit S, but also of such a Y. Okay. RSA, say N has 4096 bits, then Y will have roughly 4096 bits. So you encrypt a single bit by 4097 bits. This is not something that practitioners are happy about. There are much more efficient constructions, but we are interested in, but they use some similar ideas. Okay, and we are interested in the general assumption constructions, but this really is, they use trapdoor permutations and they use them in a slightly more clever way. Okay, good. And our theorem is it does have, the encryption scheme has indistinguishable encryptions under chosen message attacks. Under chosen plaintext attacks, sorry, not message, chosen plaintext attacks. And I think I can still manage the proof. Are there any questions about this? It's a kind of neat construction. It's similar to everything that we've seen so far, right? You have two components. The first one components helps you to get rid of the second. This is like you hide this M with this hardcore predicate of X. And you get here additional information that helps you to get rid of the hiding, of the masking. But here we have the additional property that we need this separation into public and secret keys. But other than that, this is very similar to what we did in private key encryption with function families, keyed function families. But because of the way, because of this public key and secret key business, we have to do it differently. But the overall picture is the same. Mask the message, include something that somebody with a secret key allows to recover, get rid of the mask. That's what we do. So proof of theorem 10.50, no, 16. Let A be fixed but arbitrary adversary against CPA security of pi. Construct, we know what this again, construct adversary A prime against hardcore predicate HC for pi 1. So given an adversary against this thing here, we construct an adversary that recovers hardcore predicates. And the way we do that is very similar to what we saw in previous security constructions for private key encryption schemes. Also there, the CPA construction. Overall, the proof is very similar. The details are different, but we do this. The CPA construction private key, we use this thing, well, if you can correctly, we check whether you can correctly decrypt. And if you can correctly decrypt, I think this is my value for the serial generator or for my serial function or whatever. Here we do the following. So this is how we define A prime. A prime gets its input 1 to the n. It gets the description parameters, so I. It gets its y in di. It sets pk to be I and simulates A with input 1 to the n and public key pk to obtain two messages M0, M1, and 0, 1. And let me immediately say, without loss of generality, I assume M0 is not equal to M1. Because it has to distinguish between encryptions of M0 and M1. If they are the same, there is nothing to distinguish. Okay, so if you want to be successful with probability larger than 1/2, you better choose M0 to be different from M1. So one is 0, the other is 1. We only have two messages, right? Okay, then we choose B and Z from 0, 1 from the random. We set S to be M, B, X, or Z. So Z is sort of our guess for the hardcore predicate. And then we return C, which is Y from here, and S to A as a challenge ciphertext. And then we do the same. When the simulation of A returns a bit B prime, we output Z if B is equal to B prime. So if it is successful in decrypting, we think, okay, then this must have been a correctly formed ciphertext or correct ciphertext. And a correct ciphertext means that that should be the hardcore predicate. So that's our guess for the hardcore predicate. Then Z is our guess for the hardcore predicate. If it's not equal to B prime, then we guess that the complement of Z, so that non-Z is our value for the hardcore predicate. Yeah? So this is our guess, and then we check the guess. And the checking the guess is, can you decrypt? If yes, we guess that this is the right one. If not, we do the opposite. Okay. Turns out that we really have to do that this way. Okay. Okay, let's say. So assume that an epsilon n is the probability that A out up A is A comma pi of n is 1. Okay? And we want to analyze the hardcore predicate of the probability that our H prime computes the hardcore predicate correctly. So we want to analyze this probability, the probability that A prime on input I, comma, what did I say here, Fi of X outputs HCI of X. Which is we partition it. So what is this thing doing? This is a probability that B is equal to B prime and Z is equal to HCI of X. We output the right thing if, well, B is equal to B prime, then Z must be HCI of X. That's the one case in which we output correctly. The other case is the probability that B is not equal to B prime and Z is not equal to HCI of X. In this case, we also output the right thing. Because in that case, we output the negation of Z, which is the same as saying it's not HCI of X because they are bits. Right? Good. So let me just move this here. Like a horror movie. So, how can we do that? So let's look at the probability, this probability, this one. So probability B is equal to B prime and Z is equal to HCI of X, which is probability B is equal to B prime conditioned on Z is equal to HCI of X times the probability that Z is equal to HCI of X. Conditional probabilities. This is 1/2. This is 1/2 probability B is equal to B prime conditioned on Z is equal to HCI of X. But if Z is equal to HCI of X, then what A gets here is a challenge as in the eavesdropping game. Because then this is a correct ciphertext. Okay? So this here is the probability that in the public key dropping game A I of N is 1. Okay? Which is epsilon. Okay? Good. So that's the easy case. Turns out this is not much more different. And there now I will use bits. Well, actually, so far, even in the constructions, I use bits, right? Hardcore predicate. Yeah. Yeah.
And you have this, but where's the one?
Oh, sorry. It's okay. It was missing. 1/2 sometimes disappear. I will prove that this here is also 1/2 epsilon. Okay. And the way we do that, let's see what we get here. In the case that, now we are in the case that is not equal to HCI of X. Okay. Okay. Now, if I look at this thing here, MB X or not Z, this here is HCI of X, right? This is HCI of X, right? Because I'm in the case where these are not the same. Okay. I assume that B's M0 is different from M1. This here is the same as MB bar, so not B, X or Z. Yes. I do the negation down. If I negate this here or this here in in an XOR, I get the same result. But the negation of this here is M not B. Right? So just playing around with these things. And that implies that the probability of B equal to B prime, this is 1 minus what I want, conditioned on Z not being equal to the hardcore predicate of X. Eventually, I want this to be not equal, but what I'm interested in, 1 minus this. Okay? This is the same as the probability of B not being equal to B prime conditioned on Z being the hardcore predicate of X. So I just sort of the inequality I push in here, which you can easily check yourself, follows from this equality. Take some manipulating, but this here is 1 minus the probability that B is equal to B prime conditioned on Z is equal to HCI of X, right? Yeah. Which means that the probability this here 1 minus this here, so probability B is not equal to B prime condition Z is not equal to HCI of X is 1 minus the probability B is equal to B, which is here. The probability B is equal to B prime conditioned on Z is equal to HCI of X. Okay? And that gives me another 1/2 plus epsilon. So we saw that this here, we also had to analyze the case where this is not equal, right? And this gives me, I can do the same thing, and that gives me another 1/2 plus epsilon. Yeah.
The epsilon, I believe the epsilon shouldn't be there because you are not in the case where you have the -1/2 at the end. So the probability of public key swapping should be around 1/2, right?
Where? I see that it is hard to read everything.
Yeah, in the third row.
Yeah.
Yeah, this probability of public key swapping is roughly 1/2, and therefore it's not negligible. But apart from that,
this should be the probability. No. I have here the advantage in here. Yeah, I have to deal with that. Yeah, sorry. Yeah, I forgot that. Yeah.
everyone knows what's meant by.
This is 1/2 of the. If I ignore absolute values. And the same I get from here by these manipulations. I get another one where I talk about the case where B is not equal to B prime and Z is not equal to HCI of X. So, and it all hinges on this. Also, here I use this bit manipulation stuff. But other than that, the proof goes to. Yeah, maybe I write it down. You see it in the lecture notes there, it's written correctly, but it's really whatever what you said. I need to. Okay. So and then we combine this with theorem 10.6, and we get our beautiful result that public key encryption scheme CPA secure exist if trapdoor permutations exist. Okay, good. Next time we talk about hybrid encryption and about CCA security. Here's, by the way, how you do encrypt longer messages. And okay, maybe I'll go back over this next week. For RSA, there are several improvements that you can. Okay, good. Any questions? Okay, good. Then that's it for today. Thanks.